Good afternoon and welcome to the Europlanet Science Congress 2022. We're live here in Granada. This is our first press briefing of the week and we have two back-to-back. So first of all, we're going to start off with a press briefing entitled ESA Hera Mission, Investigating Binary Asteroid 65803, Didymos in the Dark Crater, but we're actually going to be hearing all about the DART mission, about LICIACube, about Hera, and about modelling of Dimorphos, the target of the impact next week. So we are a week away from the impact, and I am delighted to welcome Andy Rivkin, the DART investigation team from Johns Hopkins University, who will start us off in this briefing and give us an overview. So Andy.
Okay. It's a pleasure to be here. Well, it's a pleasure to be, I guess I'm at home. It would have been even more of a pleasure perhaps to have been there in Spain with you in person. But I'm here to talk about the double asteroid redirection test, DART. As Anita said, we're going to be, the spacecraft's going to be arriving at Dimorphos in a little under 179 hours. 179 hours minus 5 minutes. So let me make sure I'm clicked on the right thing here. This just kind of shows an overview of the mission plan here. Of course, we launched last November from the Vandenberg Space Force Base in California. We are going to arrive, like I said, at just a little before the 26th turns into the 27th in UT. It'll already be the early hours of the 27th for most of Europe. We are carrying an Italian CubeSat, which you'll be hearing about after me, and we are going to impact the asteroid or the moon Dimorphos, which is a moon of the larger asteroid Didymos, and then we'll be observing the results from Earth. Basically, the point of the DART mission is right there in the name. We're going to go to a double asteroid. This is the binary asteroid, Didymos and Dimorphos. We are going to change the orbit of Dimorphos around Didymos, redirect it, and this is a test. This is an experiment at the kinds of scales that we want to use or that we might use if we ever needed to deflect an asteroid for real. And then down there in the lower left, we're going to observe the results from Earth. This is an international mission, as noted. So I just we put together some of these materials in languages other than English, since everyone's meeting in Spain. I thought I would show this one. Hopefully, this animation is working from the Earth. Didymos and Dimorphos are both too close together and too small to be seen as more than just a point of light. So up here in this animation on the top, you can see this model, this computer, animation of these two objects. Down at the bottom shows how we're going to be making these observations. Since they only appear as one point of light to telescopes, we're going to watch the brightness of that point of light go up and down as Dimorphos goes behind Didymos. The brightness drops a little bit. It comes back up when it reappears. And then when Dimorphos moves in front of Didymos, we can see again a brightness drop due to the shadow. By measuring this brightness go up and down, we'll be able to measure the period that it takes, the amount of time it takes for Dimorphos to go around Didymos. We've been making measurements like this for years and years. So we know very well how long it takes to go around Didymos before we show up. Once DART changes the orbit of Dimorphos, we'll then continue making these measurements and be able to compare the before and after. We have telescopes available all around the world and in space that are going to be used to make these measurements. In fact, we have telescopes on all 7 continents that are going to be involved and or have already been involved. We have Hubble Space Telescope and JWST lined up to make measurements at around the time of the impact. And in fact, I'm going to particularly give a shout out to the JWST folks who've really done an amazing job in designing observations that could be made with JWST, which wasn't necessarily designed to make observations like this. And then the Lucy spacecraft is also in the neighborhood. It's going to be doing an Earth gravity assist on its way out to the Trojan asteroids. And since it's in the neighborhood, we're going to be able to make some measurements with the Lucy spacecraft as well. I think that might be my last note. I have one more slide. So this just shows, again, we're going to be showing up a week from today. This will be, coverage will be available via the sorts of channels you expect, NASA TV, NASA YouTube, Facebook, and Twitter. And the coverage on those NASA stations is going to be from starting about an hour and 15 minutes before the impact to about 15 minutes after. So 6 p.m. to 7:30 p.m. Eastern time. It shows the UT time there. And again, in Europe, it'll be a couple hours after that UT time. So those are the slides I have, and happy to pass it off to the rest of the gang.
Hello, everyone. So a few words for LICIACube. Actually, it was mentioned by Andy. What is the idea of this mission? This is actually LICIACube stands for Light Italian CubeSat for imaging the asteroid. It's actually CubeSat, Italian CubeSat mission that is financed by Italian Space Agency, and actually is part of the NASA mission DART. So practically we were launched together. And actually on 11, after 10 months of cruise, on 11 of September it was deployed by the DART, and practically it was traveled like a piggyback together with DART. And what is the idea of this? What is the idea of this spacecraft? Actually, it's a CubeSat. There with 2 cameras that you see in a while. The idea is that we want to image, actually, to photograph the impact. What practically DART will do. DART will perform this kinetic impact on Dimorphos. And after that, the evidence that this happened and what is happening with the plume that will happen after the forming the crater, because actually what is happening in few words, what is what we're expecting. There will be impact, there will be change in the trajectory. We expect a short period of 10 minutes of the trajectory of Dimorphos. There will be a crater formed, and after that there will be ejector that will propagate in space. And LICIACube practically will, evidence will photograph this. So imagine 2 cameras that have different resolution. So now you can see on the next slide how actually it look like. How it look like. Practically, it's there are 2 cameras, Leah and Luke. They have a good resolution. So one is narrow angle camera, the other is broad angle camera, and one of them it has the resolution of 1.4 meters per pixel, the other is 5 meters per pixel. And what we have, what is the idea? So here you can see actually the cameras when they were producing in Italy. Can you go to the next slide, please? Yes. And here what you see is the timeline of the mission of LICIACube, the observation. So which were the main thing that we want to perform. We start mainly for 45 seconds before the impact, and we'll continue about 3 minutes after the impact. We'll have 3 groups of target observations. So the purposes are first DART impact observations. So the Leia camera will perform and will shot 5 images before the impact and 5 images afterwards. After that, we'll have ejecta observations and plume evolution and forward scattering. So practically, we'll have cameras that work. And after that, we'll have high resolutions observation. And in the end, we want to also photograph the non-impact hemisphere. And practically, the idea is to get about 240 images. But the main one are, of course, the impact. The closest approach to the asteroid will be about 55 kilometers, and we can evidence the impact. What we are doing with different, we do different studies. Of course, this mission we know that has also some scientific objectives. It's not only to test deflection, but also to get some information for the asteroid binary. And what we'll study the high resolution images, where we can get the best spatial scale at 1.38, as I mentioned, meters per pixel with one of the camera, and we can study the multicolor data to constrain the surface composition and heterogeneity of the target. At the same time, we are performing modeling in the group, which want to understand how actually this ejector will propagate, what is the optical thickness of this ejector. So we really want to know the crater that is formed, will be formed, and the ejector that will propagate, what will happen there. And after that, this is just to move a little bit, like introduction topic for Michael. After that, here, after 5 years, we arrived to see what is happening there, not only with the binary system, but what is going on with the dust distribution around it.
Yeah, Michael Küppers, I'm the project scientist of the Hera mission, and talking about the Hera mission, next slide. We heard about NASA's DART impacting Dimorphos, taking the LICIACube with it for the observation of the impact itself and the change in the period of Dimorphos around Didymos will be measured from ground-based observers. But that is not the end of it. A couple of years later, in 2027, the Hera spacecraft will arrive at the asteroid and will investigate in detail the two asteroids, Didymos and Dimorphos. And in addition to the additional knowledge about planetary defense, also provide asteroid science, as this is the first time that we are visiting a binary asteroid. Next slide. So this is a sketch of the Hera mission. It will be launched in October 2024, will fly by Mars and arrive at the asteroid in early 2027. The operations at the asteroid are to a large part drawn from Rosetta. So there will be first a global investigation of the asteroid from a safe distance of 20 or 30 kilometers to get the global parameters, the shape, the mass, the volume, and then getting closer, the detailed investigation will be performed. And Hera also carries two CubeSats with it. So to give you an idea, the CubeSats, both LICIACube and the Hera CubeSats, are about the size of this laptop, a bit higher, but about the surface of this laptop, and they will perform their own autonomous operations around the asteroid system. So we have this detailed characterization phase of both Hera and the two CubeSats, and then the mission will continue with getting closer and closer with close flybys, and at the end, all the spacecraft are foreseen to land on one of the asteroids, the CubeSats on Dimorphos, on the Moon, and Hera itself on the larger one, on Didymos. So what is Hera? Hera is doing for the planetary defense. One is to measure the mass of the Moon, but we know quite well already now the mass of the primary. We don't know the mass of the Moon, and we need it to be able to evaluate how efficient the momentum transfer from the spacecraft to the asteroid is, so how efficient the asteroid is deflected. Then there's the overall characterization of Didymos and Dimorphos, and this we need to be able to extrapolate the result from the impact of DART on Dimorphos to another asteroid in case we really need this technology for the real thing. Then the study of the DART crater. We have here the unique opportunity to have a crater where we exactly know the properties of the impactors. We don't see many craters on the Moon, on asteroids, on moons of other planets, but here we know exactly the mass, the shape, and the velocity of the impact, which gives us a great opportunity to study the impact process to greater detail than it can be otherwise. And finally, this again goes into the efficiency of the impact. We will also see some tiny details of the rotation of Dimorphos, as it is possible that some of the energy of the incoming impactor of DART may not go into changing the orbit of Dimorphos, but into make it tumbling, into creating libration and all kind of ways of dancing around. Those are the main tasks for Hera for planetary defense. Next slide, please. And But Hera also is important or can provide important contributions to asteroid science. It's the first mission to a binary asteroid, which may us help to learn more about how those double asteroids form and evolve. It is also visiting the smallest asteroid ever studied, and this is important because for asteroids smaller than about 200 meters per second, we are in a completely different regime. The evolution is really driven by the internal strength of the object and not anymore by the self-gravity as for the larger objects. Finally, one of the CubeSats is taking a radar with it. So it's the first radar investigation of an asteroid, which allows to study the interior structure of the two asteroids, which is also a really new investigation. And those are the first CubeSats that navigate at a small body. So many firsts in the Hera mission, in addition to its contribution to planetary defense. And with this, I believe we hand over to Adriano and some more details on the science with Hera.
Just a moment while I get up your science. Actually, in the meantime, Callum, do you have any questions from the floor?
We do. Thank you.
Yes, please.
So from Megan Bartels from space.com for Stavro, could you give an update on LICIACube since its deployment? What has it been doing, and does everything seem to be nominal? Can we expect any preliminary images before the impact?
Okay, thank you for the question. Yes, everything is nominal. The LICIACube is in good health. We have to perform actually a few maneuvers. There is only one particular that it was performed. It was practically we have to make some adjustment to be on the right trajectory, and this is what is going to happen. Practically, we'll perform also some calibration, so we'll shoot some images that after they should be calibrated. So regarding the images, yes, we'll get, for the images after the impact, we need some period of time. It will be about 6 months to download these images. It will take time, but the first images, they will be ready immediately, so practically very close after the impact. So we'll have a download directly from the spacecraft to the Earth for the images of the impact. This is what we'll have, yes.
Slightly related to that, in terms of just the raw data, how quickly will we get any data at all from the DART mission once it happens on Monday?
So maybe Andy could answer to this directly regarding DART data download.
Sure. And so the question I thought I heard was getting data downloaded from DART. So the images, we have one camera on board DART, which is going to be both what feeds into the onboard autonomous navigation and also are what gets used to kind of interpret the surface of Dimorphos. Those images come down, obviously before the spacecraft is destroyed. So those we plan to be showing on the NASA TV broadcast as they come in. And then in terms of turning things around for, so the images themselves are available. I think we're still trying to figure out an exact schedule for that, but I think we anticipate that those should be, at least some of them should be ready pretty quickly. And then the non-Draco is the name of the camera, the non-Draco images, the ones that are taken by, say, the Hubble Space Telescope or something like that, we're going to get those down and analyze them. But I'm sure that there's a lot of interest in making sure that we can turn things around as quickly as we can. So I can't give you an exact date, but hopefully we'll have a better idea soon. Some of these observations are still getting finalized.
Brilliant. Okay. So thank you. And finally, we are moving on to Adriano and Campo, who will be talking about modeling.
Okay, thank you. Yeah, my name is Adriano Campo Bagatin from University of Alicante in Spain. And yes, I will try to tell about modeling of these complicated systems. So when it comes to modeling, is that part of planetary science and any other science, of course, that starting from available knowledge, you try to make predictions of what is going to happen on how a system will evolve. So in this case, our knowledge is limited. It is not zero, but for instance, we have here a shape model of Didymos, the main body, and we have a shape model of Dimorphos, one of the possible shape model of Dimorphos. We don't know much about Dimorphos. We can say that it is maybe approximately like a three-axial ellipsoid, but we are not sure of what is its exact shape. It could be anything of those that is on the slide. It could be elongated, could be very coarse. We don't know. So this is one of the many uncertainties that we have when we want to predict the outcome of the dark impact. There are many unknowns, and there is an unknown influence of what is. We don't know what the impact angle will exactly be. We don't know what is the slope of the area where the impact will happen. This may have consequences on the outcome of the impact. We don't know what is the ground texture of the asteroid. We don't know if we are hitting a boulder or not. This may change the outcome again. We don't know what is beneath the surface. Even the shape of the DART spacecraft or the attitude with which it will impact the object may change the outcome. And of course, starting from some experimental point, we can improve all those models. And the experimental point is this mission. That's why it's so important to have this mission, and it's important to have Hera 4 years later to study in detail the system, how it is. Next, please. Yeah, in fact, we may even not have a crater. It is one of the possibilities. There are studies that are assessing that, depending on the structure of the object, instead of a crater, we may find a deformation of the object itself. Next, please. Yes, so it is very important to try and understand the internal structure of this body of asteroids in general, but in particular of targets of space missions, in particular for space for Earth planetary defense. And this is what we are doing. Obviously, I can't summarize all the models that are going on around the world because it would take too much, and probably I'm not enough knowledge. But I can summarize in what way we are trying to contribute to these missions from the Spanish institutions that are involved. In particular, there are many institutions in Spain that are involved. It's the Instituto Astrofísica de Canarias, which is involved in observations. There is a group at the CAB INTA in Madrid that is involved in cratering experiments. And we are trying to help in the modeling part. And in particular, we are trying to model the internal structure to understand what is the size distribution of the fragments that may form this object. But please remember that this object may also be just a coherent single rock instead of a rubble pile. And we have been studying the effect of the impact on the transmission of momentum and energy inside the body. And yes, this may also cause a low speed ejecta, and this low speed ejecta may form a tail after the collision, and may even somewhat reduce the possibility of taking pictures by LICIACube, and it will be an important information. If we have some extinction due to the dust that is coming out at low velocity from the surface of the body, we will have information about what is its surface composition, structure. Next, please. Yes. This is just some predictions of what the tail that may be observed in the weeks after the impact is. Next, please. And finally, there is also the possibility that we may find a cloud of debris around the asteroid while the spacecraft are approaching it due to the fast rotation of the primary. But this, we are also studying the dynamical behavior of those particles that are trapped in the gravity field of the system after the impact. And okay, I think I'm done. Thank you.
Yes. So Yanis Murakidis asks, when can we say that the mission was a success? What are the minimum targets?
Yeah, sure. I'll take this one, and I guess I'll say I would be happy to put my camera on, but I don't seem to have permission to put my camera on. So as far as the DART project is concerned and NASA is concerned, we have 4 things that we need to achieve to be considered a success. We need to impact Dimorphos this fall. We need to be considered a full success to get the A+. We need to impact Dimorphos this fall. We need to have the DART spacecraft cause at least a 7.73 second change in the orbit period of Dimorphos. So 73 seconds, a little over a minute. We need to measure the change that was made by the DART spacecraft to a precision of 7.3 seconds. And then we need to come up with an estimate of how the momentum of Dimorphos changed relative to the momentum that the DART spacecraft had. Those are again kind of to meet what NASA expects of us. Some of those will take a long time. We're going to probably take weeks, potentially to maybe even months, before we get the precision of the orbit change to 7.3 seconds. We'll know pretty quickly whether DART hit or not, and then we'll have a much looser idea of the period changed much sooner than weeks to months. So I think we'll know pretty soon whether kind of in the broad sense how well the mission was a success, whether we hit how much of roughly how much of a period change we caused. But the T in DART is for test. So some things that might not so we're open to a lot of different outcomes being interesting and helping us understand the planetary defense implications of what we're doing.
Do we have any questions from people in the room? Do we have from everybody in the room? Yes, hi.
My question is for Andy. Actually, when you were planning the orbit change, how did you define the 7.3 seconds? What's the rationale behind it?
Did you hear that, Andy?
Where did the 7.3 second precision come from? That's the question. Yeah. So the idea when we were first discussing what requirements would be appropriate was we thought that we could measure that it would be reasonable to say that we wanted to measure a 10% difference in the position of Dimorphos a month after the impact. That if it were in a place that was 10% different from where it would have been otherwise, that we could measure that after a month, that seemed reasonable. And then you crank the numbers, and that turns out to be a 73-second change in the orbit period. And then we said, okay, knowing that number to a 10% precision seemed like that would be a useful, a good thing to shoot for. So that's where the 7.3 seconds comes from. It comes from the 73, and then the 73 comes from giving us a month to make what we thought was a measurable change. We think that the real change is going to be much larger than 73 seconds. We think it's probably going to be more like something more like 10 minutes. It could even be more. But the 7.3 seconds remains the precision that we're going for. We're not going to say, well, if it's 10-minute change, we're going to go for 10% of that. We're keeping the 7.3 second.
Thank you. And then Helen, we have one more online.
Yes, one more from Dan Fisher. Can we expect effects on the orbit of Dart and LICIACube by Dimorphos, which are large enough to be measured through radio science, so we'll get at least a rough mass range?
I
don't know if that one's for me too. I'm happy to try it.
Maybe I'll comment after that, because it's a tricky question actually.
Yeah, the usually the way the kind of typical radio science measurements work for mass is that if you are coming in fast, then you need to pass very close to your object, and it needs to be massive. And if you're, if it's not massive, then you have to come in really slow and really close. And unfortunately, the combination of those does not work for Dimorphos. Dart is coming in too fast, and Dimorphos itself is too small. And I think the same is going to be true for LICIACube. So even though it's missing, I think that basically Dimorphos is too small for the speed LICIACube is going to pass by. So we're not going to be able to get a radio science measurement.
Yeah. Maybe I can add to that, even for Hera, which will rendezvous Didymos and stay half a year close to the asteroids. According to our simulations, the more accurate method to measure the mass is the wobble of the primary due to the presence of the secondary, because for the radio science, even there the gravity field is very much dominated by the primary.
Do we have any more questions? Okay, we are actually almost up to time for this first half of this press briefing. So I'd like to thank very much Andy, Stavro, Michael and Adriano for their contributions today, and wish them luck with the Dart Impact next week and all the missions going on. Thank you.
Thank you.
Thank you.